Hello everyone, this is a video for Intro Stats, Unit 10 on sampling distribution. So the very first lesson is what is a sampling distribution? And I'm going to go straight into the exercise. It says here bias or and actually bias and unbiased estimator. All right, student view. I should switch off. So let's dive in. All right, Isabel um, was curious if sample maximum was an unbiased estimator of population maximum. So she started with a large, normally distributed population of test scores whose maximum was 99 points. Right? Maximum was 99 points. Excuse me. Then she took a random sample of 6 tests and calculated the maximum of the sample. She replaced those tests and repeated this process for a total of 40 trials. So if you count all the dots here, you should be able to see 40. There are 40 dots here, right? There are 40 dots. Now each dot represents something. It's a maximum. Each dot here is a representation of a maximum of the sample. So you have 6 tests. So test one, test two, test three, test four, test five, and test six. So test one, test two, test three, test four, test five, and test six. So those 6 tests are randomly picked from the population. And then from here, right, you pick the highest one. So the maximum. You pick one that is maximum, right, out of the 6 tests. And then you put that value here on the dot plot. So sample maximum. So each dot here is a maximum of 6 tests. Each dot here is a random. It's a maximum of 6 tests for that trial. So they're all amps. They're all maximum of the 6 tests in that trial, and there are 40 of them, right? So imagine they're all amps. They're all amps. They're all maximum. They're all maximum of a trial, right? And each trial consists of 6 tests. So if you can understand this, and that's the whole idea of a sampling distribution. So in this case, they're sampling for the maximum. Now you can use sample mean. Yes, you can. Can you do a sampling distribution for the minimum? Yeah. Can you do a sampling distribution for the mean? Yeah. Can you do a sampling distribution for the median? Yeah. So there are sampling distribution is very powerful. You can do a lot of things, but the whole idea is from the population, you are taking samples of a certain number and you keep taking the same number of samples. So let's say if you have right now in a school of 3,000 students in Granger, if I want to sample 100 kids, right, and I want to see what's the proportion of kids who like school lunch, right? So, and then I take the first 100 kids and hey, do you like school lunch or you don't? Then I keep getting that data, and maybe out of the first sample, maybe 30% of the kids like school lunch. Maybe that week wasn't a good school lunch. Anyway, so you have zero point 0.3, right? Zero point 0.3, and you put that into a dot plot. 0.3 will be a 1 dot, but that dot represent, right, the proportion of that sample of 100 students. Then I put that 100 students back into the population, and then I repeat the same experiment. I randomly pick another 100 students, and then I ask them, do you like school lunch or not? Then I find another proportion of kids. So in second time, maybe 0.7. Maybe that day school lunch was really good. Some of the kids really liked the school lunch then. So you see how it varies, right? So therefore, it can produce a distribution. So I hope you get that. And if you don't, please rewatch the videos and come and see me if you have any questions. So based on these results, does the sample maximum appear to be a bias or an unbiased estimator of the population maximum? So population maximum is 99, right? Here we were told that the normally distributed whose maximum was 99. So the mean is at 99 right here. The mean is right here at 99. But yet, all the samples that we collect, right, their maximum did not even come close to 99. Okay? So sample maximum appears to be a bias. So it's biased. It's not even close to the actual population maximum. Here it says the population maximum is 99. Now, if it's unbiased, all of this, all of this, if it's unbiased, all of this should move so that the mean should be here, and here in the middle should be 99. And that's what unbiased means, that the distribution, the mean in the middle, mean should be close to the actual population parameter, right? Should be close to it, but that's not this. For this case, it's not even close. Okay, so based on these results, it appears that it's very, very less, right? It's less than 99, so it underestimates the maximum. Sample maximum appears to be a biased estimator since it's consistently underestimate the population maximum. Okay, so now look at the dot plots. The dot plots below show an approximation to the sampling distribution for three different estimators. So, right, um, so if you look at statistics A, this is, you see all this is pretty bunched up, right, for statistics A. And the mean is about 4. Why do I say 4? Because this is where the highest point is, the peak, right? It's about 4. And it's pretty bunched up. That means when it's bunched up like this, it doesn't have, it has low variability. Now, high variability, you're looking at statistic C. See how it's spread out, right? This is high variability. But what's the mean here? The highest point peak here, the mean is 2. Compare B and C. You see how B, the peak is also 2, but it is less varied, right? Less variable, less variability. So for any sampling distribution, the mean should be close to the population mean for it to be unbiased. So here, if the actual value of the population parameter is 4, they tell you now that the actual population parameter is 4. So 4 happens to be this one, right? 4. So statistics A is spot on. Not only does it have the mean of 4, which is the same as your population mean, right? It's the same as your population parameter. It has low variability. So that's what we want. But let's look at the question. Which dot plot displays the estimator with high bias? That means it's not even close to the population mean and has low variability. So only B and C. B and C, the mean is 2. So it's different from 4. I will pick B and C, but compare B and C, which one has low variability? And the answer is B, right? B has a low variability. Okay, Sergey, or Serge, was curious if sample third quartile, right, for or Q3 was an unbiased estimator of the population third quartile. So in this case, it's a population of third quartile. He started with a large normally distributed population of test scores whose third quartile was 80 points. Okay, so 80 points is about 78, 79, 80 is right here in the middle, right? Right here, 80. He then took a random sample of 6 tests and calculate the third quartile of the sample. He replaced those tests and repeat this process for a total of 40 trials. You should have 40 points here. And each point just means right? Each point just means that you have 6 tests: test 1, test 2, test 3, test 4, test 5, and test 6. And then from all these 6 tests, they calculate the third quartile of the sample, right? So all the values here, right? All the values, they find like a box plot, all right? They compute into a box plot, right? Box plot that someone looks like this. This is the minimum, this is the maximum, and this is Q1, this is Q2. Q1 means first quartile, Q2 means medium or the second quartile, and this is Q3, the third quartile. So every 6 tests, right, they randomly pick 6 and then they find the third quartile for this 6 tests. And that value, they put it here. So here, just imagine all those dots, they are just third quartile of a trial, right? And there are 40 trials. Okay, so here the mean, they said that the is 80 points. The third quartile is at 80 points right here. Okay, see what the question is asking then. Based on these results, does the sample third quartile, right? All these are samples. Sample third quartile appear to be biased or unbiased estimator of the population third quartile. Okay, since it's in the middle, right? Since it's in the middle and you see all the distribution is somewhat in the middle, you can say that the sample third quartile appears to be an unbiased estimator, right? As long as it's in the middle, it's not skewed, it's not, to the left, there's not much more on the left, not much more on the right. It has to be what I would say symmetric. Okay, so if this is right, if this is your population mean, if this amount is the same as that amount, is symmetric, and we can see, even though there's a little bit higher here, right, the peak here at 80 is less than the peak here. However, because it's in the middle of the distribution, right? Now, I'll be more worried if you have something that looks like this. Now, if here is your population parameter, is this centered in the middle? No, right? There's more here, right, compared to here. So you would say that here, right, this particular, the sample, right, the sample would be underestimating the true population parameter because there's more here, which is less. It always underestimates. But if you have more, so let's say if you have, so if your population is right here, you see how there are more here compared to a few here, one here. So you would say you are overestimating. Okay. All right, let's see. So, okay, Matilda was curious if sample interquartile range, this is another sampling distribution on interquartile range, was an unbiased estimator of the population IQR. She placed ping pong balls numbered 0 to 32 in a drum and mixed them well. Note that the IQR of the population is 16. 16 is about here, right? 16 is about here. Notice that if it's here, everything here, right, there seems to be, the middle of this distribution seems to be here, isn't it? Seems to be in the middle here. But the true, it says here, but the population IQR is at 16. So you can see that there are more here to the left. So it's consistently underestimate, right? Consistently, it's a biased estimator, first of all, because it's not on 16. And it's consistently underestimate the population IQR. Because if you look at this, what's the mean? The mean is about 11. but they tell us that the population mean population IQR is at 16. Here, the sample IQR, right, the mean of the sampling distribution is about 11. 11 is not close to 16. And here, because 11 is less than 16, we say that it's a bias estimator, and it consistently underestimates because 11 is less than 16. So if you have any questions, let me know, and I'll post this on the Canvas. All right. Thank you very much. See you next time.